ready for the next section? No, you are not ready. I saw you have waving your hand. Okay, so our next lecture is by Andrea Thorn. I usually don't introduce our lectures, but I do exception for Andrea. She did her PhD in George Sheldon School, and then moved to Randy Reed School, and after June, she is moving now to our group. She's now going down. And she's going to talk about experimental phasing. Yes, and that's extremely important if you are doing new structures. I think knowing how to do experimental phasing, how to solve structures is very, very important.
Yeah, so I'm going to talk about experimental phasing, Pattersons, and SHELXC this morning. So I wandered around my institute and also did some effort on Facebook to find out what is actually experimental phasing. And I got a number of answers, but one was really striking me as possibly the most practical answer you can get, which is experimental phasing is what you do if MR doesn't work. So this surely holds true, but let's go a little bit more into detail what experimental phasing really is. So experimental phasing methods depend on the intensity differences. These differences are caused by marker atoms that can be heavy atoms or anomalous scatterers, or in radiation damage induced phasing, atoms that get lost due to radiation damage. MAD and SAD methods will exploit anomalous scatterers, the anomalous signal from one or more data sets, from the same crystal usually, or from crystals which are identical. SEER and mirror methods utilize several heavy atom-soaked derivative crystals, so more than one crystal is required. RIP is a special case where you have the same crystal before and after radiation damage, but the method works similar to SEER, SIR. The crystals, however, have to be isomorphous, so their major compound, their lattice packing, their lattice and their symmetry has to be very similar. These are all the abbreviations for the different methods that are all experimental phasing methods. So there is single wavelength anomalous diffraction or dispersion, which is SAD, and a special case of this is if you use the native sulfur that is in a protein to phase it, which is sulfur SAD then. Multiple wavelengths anomalous diffraction, which is called MAD, where you use more than one wavelength, as opposed to SAD. Single isomorphous replacement, SIR, where you have two crystals. Special case radiation-induced phasing, where you use the radiation damage. Single isomorphous replacement with anomalous scattering, SIRAS. What is strangely missing from this list is MIR, multiple isomorphous replacement, where you have several heavy atom derivative crystals and use their isomorphism and the heavy atom signal. And multiple isomorphous replacement with anomalous scattering, which gives you a lot of information, but is experimentally a little bit difficult. First, some theory. First thing, structure factors. By now, you should have heard about structure factors. If you have no idea what I'm talking about when saying structure factor, here's a short explanation. For each reflection, there is a structure factor, FHKL. HKL is the index of the reflection. F is the structure factor. If we know the structure factors, including their phases, for all reflections in a data set, we can easily calculate the electron density map and hence get the structure. Problem solved. So between the structure factors and the electron density, Fourier synthesis and Fourier transformation transfer. A structure factor can be seen as a wave. This wave will have an amplitude, which we call the absolute of FHKL, and a phase, which is where the peak is, where it starts. However, it can also be regarded as a vector in the complex plane. So the complex plane has its real part here and an imaginary part there, and this vector would then be FHKL. Possibly you remember from Randy Reed's lecture, he has said that vectors and wave functions can be regarded as the same. The length of this vector would then be equivalent to the amplitude of that function, would also be called the absolute of FHKL. And we can get this amplitude because its square is proportional to the intensity of the reflection. So we are going to have that information. However, the angle of the vector is the phase phi HKL, and that cannot be measured directly. This brings us to the central problem of crystallography, which is the phase problem. And this is the whole reason why we do experimental phasing. Another theory, Patterson maps. So I have to bring this because a student in our lab told me that having a Patterson map is like dragging a rabbit out from a hat. And he does not know where they come from exactly, so I have to say it. And they said there has to be a rabbit, therefore. So between the structure factors and the electron density, there is Fourier. If we look at the structure factors closely, we have now seen their actually amplitudes and phases. And if we generalize, we would say we just get a map. However, at the beginning of our experiments, we only have measured intensities, which are proportional to the amplitudes, and we don't know anything about the phases. So we set the phases to 0. If we now do a Fourier synthesis, we'll get a so-called Patterson map. What does it look like? So if we assume without a crystal lattice an electron density that would look like this, possibly being of 4 atoms, the Patterson map of this would look like this. Can you see anything that brings you from this picture to that picture? So if we look very closely, we can see an interatomic vector here between the two weakest scatterers. And this very vector can be found again here, pointing from the middle of the picture to the weakest spot in the image. There is a mirror image, or actually in the other direction, that same very vector. This holds true for other vectors as well. This is the connection between the weakest and the strongest scatterer. And this vector can also be found here and there. We can again see that the peak height here, the point to which it shows, is possibly connected with the strength of the scatter. Again, all other vectors can also be found. So the Patterson is actually a vector map of the molecule and its mirror image. We get interatomic vectors from this, which gives us some structural information, but we get no relative positions. We only get the direction and the length of the vectors between the atoms. And we can't resolve any handedness here. However, you will easily see that you get n squared minus n peaks in a Patterson map. And for a protein, that's quite a number of vectors. And given that they all come from the same origin, the area around the origin will be extremely crowded by thousands and thousands of vectors. Also, in reality, resolution is much worse usually, and reality would, in a better case, more look like this, where it's very difficult to resolve actual atoms, in particular the weaker scatterers. So resolution and the number of vectors are here a problem, and the number of vectors directly relates to the number n of atoms. I will come back to this because there's a way we can anyhow use Patterson. But for now, I'll go to anomalous scattering. Anomalous scattering So the first thing you need to know is that each of the structure factors actually sees contributions from each and every atom. So you have a structure factor from a certain reflection, and that structure factor will have contributions from each and every atom. In the imaginary plane, it may look like this. So each of the little arrows is the contribution of one atom, and the sum of all of them makes up FHKL. There's Friedel's law, and the first crystallographers believed that Friedel's law was true, or strictly true. Friedel's law says that two reflections that are centrosymmetric to each other in reciprocal space are so-called Friedel mates, and their amplitude will be the same. These two vectors have the same length, meaning the two reflections will have the same intensity, and their phase will be, the phase of one will be the negative phase of the other, and you can easily see this from this picture. This holds approximately true for most atoms in most situations. However, it is not exactly correct, and this is due to anomalous scattering, which is not very anomalous at all, because it occurs a little bit in most atoms at most times, but the effect is not very big, unless you are at a so-called absorption edge. So each of the F atomic contributions is actually composed of F0. F0 depends on the atomic type and solely on the resolution. This is the anomalous contribution to F. We split it conveniently up in a real component and an imaginary component, and we call them F prime and F double prime. And F prime and F double prime are usually observable near the absorption edge of the atom's element. And they are consequently dependent on the wavelength, because the absorption edge is only at a certain wavelength. It will typically look like this. Energy goes in this direction, wavelength goes in this direction. This is F double prime. It is at the same level, then rises to a peak, drops off a little, and goes on a higher level, coming down eventually again. F prime has a drop. So if we can measure at a wavelength around here, we can possibly maximize the effect. And this makes sense because F double dash breaks Friedel's law. So these are the two Friedel vectors. This is the Friedel pair. And the F dash contribution is usually pointing a little backwards. Not exactly backwards, but it usually points in the other direction. So this is the sum of all F dash contributions for all atoms in the structure. And this is the F double dash contribution, which is usually at a 90-degree angle. If you look now closely, you will see the length of the two vectors is not the same anymore. F double prime, the anomalous scattering, has broken Friedel's law, and we can exploit this effect to phase our structure. So here we come again for the Patterson map. A Patterson map can be calculated. Instead of using intensities, we can take differences of intensities. You have seen the Friedel mates now have different lengths, right? Consequently, the Friedel mates now have different intensities. If we can calculate the difference between them, we get some intensity difference, and we still don't know anything about the phases, so we have to set them to 0. However, we can now calculate again a Patterson map, which is called an anomalous Patterson map because it's based on the intensity differences from the anomalous scatterers. And even at a low resolution, atoms can now be differentiated because, if you think of it, you have only a few atoms in the structure which are anomalous scatterers, which at this wavelength where you measured have a strong anomalous effect. These atoms will be possibly quite far away from each other. If you think of, for example, a heavy atom soak, they are very separate from each other, so resolution is not a problem anymore, and also their number is lower. And this will allow you to exploit the Patterson map, actually, if you're very lucky to find your atoms, any way to get some information about them. So this is a picture which I got from Phil Evans. It shows an anomalous Patterson map, actually a section through the Patterson map. But if we would have a heavy atom derivative of the same crystal, we could actually calculate not only intensity differences between Friedel pairs, we could see how an intensity changes between the two data sets. Because if you have one data set from a crystal which is native and one which is heavy atom soaked, the intensities would change slightly, right? And the difference would give us an information about exactly that very atoms that we have soaked in. So we can not only have anomalous Patterson maps, we can also have isomorphous Patterson maps, which I calculated with the differences between isomorphous crystals. Another effect is that most heavy atoms do also scatter anomalously at common wavelengths, and we can also exploit that. So this is the reason why we have things like this, where we have the anomalous Patterson and the isomorphous Patterson from the same crystal. Now we come to more practical matters after having introduced all these basics, and I will talk about how SHELXC does these things. You will possibly, in the future of the course, hear also about other programs which may do these things a little differently. Phases of there's direct methods, which is another, I haven't said that. Patterson methods have originally been used to solve small molecule structures. They didn't use the anomalous signal, they just had structures that were so small and so well resolved that they could solve their structure from the Patterson map alone. And this was the very early crystallography. Another way in small molecule methods is direct methods. And direct methods exploit that the phases of strong reflections are usually related in some manner to each other. And this is a result of atoms not being scattered totally randomly over a unit cell. Actually, you cannot have two atoms at the same position, for example. Usually they have well-resolved, rather roundish electron densities for them if the resolution is high enough. And they are well separated from each other. Also, electron density cannot be negative by definition. It can only go down to 0. So there's two things you should possibly have heard about. It's the triplet equations and the Say equations. So I'm mentioning them here, and they form the basis of direct methods. These relations are relatively easy to resolve for a few atoms, and you will already know where I'm pointing here. We can use these direct methods actually when we take the anomalous signal or the heavy atom signal into consideration. Also, in direct methods, and in SHELXC in particular, we use normalized structure factors, so-called E-values. An E-value is the absolute of the structure factor squared divided by a scale factor. This is usually 1 for most reflections. Divided by the average within a certain resolution shell of reflections. So we take the average from a certain resolution shell, we take the structure factor we are looking at, we divide it by that value, and we get an E-value. This is very convenient because E-values reduce the effects that come from the moving of atoms, and in an ideal case, they would refer us to point atoms. So atoms that would have no expanse in the real space. And as you can possibly see, for direct methods and Patterson, the atoms have to be separated nicely. This is very useful. So we find the substructure of marker atoms actually exploiting direct methods and Patterson methods that we have borrowed from small molecule crystallography. These methods require separate atom electron densities to locate atoms, and they work here because the marker atoms have large interatomic distances. Disulfides. Oh, what happens to disulfides? Disulfides are relatively close, right? So they become so-called supersulfurs, which is usually a slightly elongated blob of anomalous density. And the same happens if you have put in clusters of heavy atoms. At low resolution, they just fuse into one peak in the anomalous or heavy atom map. So there's two terms which you would possibly come across. One is Patterson seeding, and it means starting to search for where actually the atoms might be in real space with atom positions that are consistent with the anomalous or isomorphous Patterson maps. It makes a lot of sense to not randomly put atoms, but just put one and then put the next one consistent with the Patterson. And then there's dual space direct methods. The direct methods will improve our idea of phases and actually allow us to have phases for all the strong reflections. And dual space means here that in real space we will do a peak search, eventually throwing out peaks and taking them into consideration, but refining the phases in reciprocal space. Both of these methods allow us for a relatively quick substructure search, and convergence with dual space direct methods is faster than in reciprocal space alone. So what we have here is an overdetermined problem with noisy data, right? We are searching perhaps for 20 atoms. We have thousands of measurements, but they are very noisy because the anomalous difference, also the difference between two crystals and isomorphous difference, will be very small as compared to the total intensity. And for the total intensity, we have an error. So some factors are absolutely critical for the substructure search. The resolution range highly affects the outcome. You can imagine that you should stop using the data at the moment the anomalous signal stops, and that will not be your natural resolution limit because you're possibly looking at 1/100th of the intensity you've measured. The reliability of your measurement ends much sooner. You have to have good data quality. If you have a lot of error already in your intensity measurement, you will not get far with these methods. In particular, if the signals are very small for the lighter elements like sulfur. Intensity outliers are hugely problematic because if you're calculating a difference between two data sets, say, and one of the reflections is covered by the beam stop, but you anyway integrate it, and in the other one it's fully there, the difference you will get between those intensities will be huge and will dominate the whole calculation. So it's absolutely crucial to look out for the intensity outliers when doing experimental phasing. And scaling, and anisotropic scaling, is also needed. However, at this stage, we could not say anything about the handedness of the substructure. We have now found marker atoms, but we don't know how they are related. So we have two mirror images and we don't know which one is correct. Usually the program will provide you with one of the two hands and throw away the other because they are really not containing any information. However, that doesn't have to be necessarily the correct hand. At this moment, you don't know anything about it. However, we have now established how we find a substructure. So and the program we have done it with is SHELXC.
Can you rotate and translate that whiteboard in correct order in mirror image?
But I will now stand in front of it, I think, anyway. So I'll take it back until I write the next thing. How do we phase the rest? So first I'm going to talk about SHELXC. we have seen that all the atomic contributions contribute to the structure factor, so we could split them up in two parts. We would take one, which we call Fa for anomalous scatterers, which would contain all the contributions from the marker atoms, and another vector which would contain everything from the protein. If we would sum the two up, we would get the total structure factor, which we call Ft. Now, if we look at those between Ft and Fa, we can assume there's an angle. We call this angle alpha. Alpha would then be the phase of T minus the phase of A, or the phase of A plus alpha would give us the phase of the total structure factor, which is what we want in the end. So if we know the anomalous scatter positions and heavy atom positions, we can calculate Fa, right? We know the phase and the length of Fa. So we have that. If we can now estimate alpha, we can get the total phase and would have solved, at least initially, the problem. Another way, and this is assuming that we have no errors. You will be given in the end of this week another lecture by Ali McCoy. She will show how to treat things if we assume we have errors. This is an ideal equation given we have no errors, and I'm afraid it looks possibly a little complicated. So you can see that here is for two Friedel mates, their intensity. There's three factors, A, B, and C. They are dependent on the F prime and F double prime contributions. So you have seen that those F prime and F double prime contributions depend on the wavelength, right? And we can possibly estimate them theoretically. We can also eventually measure them. So we would know these for the given wavelengths at which we took that data set. However, the total structure factor, the marker substructure structure factor, and alpha are unknown. So what happens is we have, for each wavelength that we have measured, we have different A, B, and C, and we have two observations. We don't know Fa, Ft, so the absolute of Fa, the absolute of Ft, and the alpha. Means we have three parameters, and we have two observations from each wavelength. So if we have measured two wavelengths, we'll have four observables for three parameters, and we can solve the problem mathematically. And this would work best if F dash and F double dash values would be very large in our data set. And we call this then MAD, multiple wavelength anomalous diffraction. However, you all know that we can also do SAT, and the question is, why can we do SAT? We only have two observables because we have measured only one wavelength. So we have to assume that the length of Ft will be the average of FHKL and its Friedel mate, and consequently get this. And that is sufficient to make an initial assumption about the total phase. I'll show that again graphically. You have a protein contribution, you have an Fa contribution, but this is only the Fa contribution now for F0. So there's no anomalous signal yet. The anomalous signal comes in now, and it's all the F prime contributions, and then all of the F double prime contributions. And this is, again, the angle alpha. So what you can see is that in this case, F double prime points slightly in the direction of Ft. To make it more clear, we have a measurement. We know the length because we know the intensity of two Friedel mates. But we don't know their phase. However, if we observe that the absolute of FHKL is much bigger than the absolute of its Friedel mate, then that must mean that we have a situation like this. We have F dash f prime pointing slightly backwards, and f double prime pointing approximately against the direction of the original structure factor. Again, here we have the original direction of the structure factor, and we can see that f double prime points slightly in the direction of them, making f HKL very large and f minus h minus k minus l rather small. The resulting structure factors would look like this. So the alpha angle in such a situation would be near to 90 degrees. If we see a situation like this, where FHKL is much bigger than its Friedel mate, it means that f double prime has to point in the same direction as FHKL. It also means that the Friedel mate's f double prime contribution has to point in the opposite direction. Alpha must consequently be close to 90 degrees, so we have an idea what alpha could be look like. You can see it's very rough. If we have the opposite case, alpha must be close to 270 degrees. So the reflections with the largest anomalous difference must have either alpha near to 90 degrees or to 270 degrees, depending on which of the two is larger. Consequently, yeah, as you can see, the estimation is very rough. I mean, we really don't know whether it's 100 or 110 or 90 or 80, but approximately. There's one other case. Has someone an idea what the case that I haven't discussed yet is? For strong reflections, we have now seen what happens if FHKL is much bigger than its Friedel mate. We have seen what is if the Friedel mate is very big as compared to FHKL.
If they're the same?
Yes, thank you.
Less, more, and same.
Yeah, if they're more or less the same. We know that the f double prime contribution must be very small, that can be, or it is almost perpendicular to the structure factor itself. So consequently, alpha must be close to 0 or 180 degrees. However, we don't know which of the two, which cannot be resolved at this state. We need density modification to resolve this. Phi t can now be calculated because we have estimates for alpha and we have found the substructure. So I can rotate and translate and say we have estimated alpha. SHELXC does usually do that for us. So we have initial phases. However, we need in most cases to apply density modification because of the inherent errors, and in SAT because we haven't resolved that 0 and 180 degrees issue yet. And in addition to all of that, we still don't know about the handedness. So the phases can be called ambiguous. And density modification is based on the fact that protein or macromolecular crystals will contain lots of disordered solvent. They will have ordered regions, which is usually the protein or the structure you're interested in, but they also have disordered regions. And these disordered regions are relatively uniform electron density. It has not very high peaks and it doesn't have very strong holes. It's not very structured, while the protein will be a very peaky region of distinct electron density features. And that can be exploited. Also, some programs use NCS averaging to a great advantage to improve the map quality, and a high solvent content, while it usually means some other problems earlier, here gives the better improvement. In SHELXC, which is the program for density modification within SHELX, we use the sphere of influence method for density modification. And I'll just give it as an example for density modification. So you have calculated your map with your initial phases. Yeah, you had the intensity measurements, you have the phases, you can have the amplitudes, and calculate an initial map. You ask yourself if a certain position within that map is an atomic position. You draw a sphere around it, and this sphere has a radius of 2.42 angstrom. Why 2.42 angstrom? It is the typical one free distance within a protein. So if this is an atomic position, we expect that on the surface of the sphere there might be other atoms. We plot the electron density on the surface of the sphere, and we look at how much does it vary. If it doesn't vary very much, we flip the density. All the positive peaks become negative, or the negative peaks become positive, and because of some calculation that we do later, after a few cycles, this will end up in a flattened area. If it varies a lot, like here, we sharpen the density, making peaks higher and gaps lower. Because you can clearly see, if you see a distribution like this, you possibly expect 3 other atoms on the surface of the sphere. And this initial position is very likely to be an actual atomic position of protein. After several cycles, this means flat, disordered solvent areas and very peaky, good protein or macromolecular areas. However, you do that for 2 hands, for both hands of your substructure, for both enantiomers, and you choose then the one which looks like protein. So I've brought an example so you can know what I mean. So this is one potential substructure, and one of the maps we get looks like, there we are. Looks like this. You can see this map is relatively ragged. Can you see it good? It's relatively ragged. We are not so sure what is going on in here. That could be protein. The other map looks like this. And you would think that is a protein. It has higher connectivity. We can see side chains already.
What is the resolution?
1 point something.
You will not see in your slide.
I just wanted to choose an example, but it's very clear what I mean. You see roundish density here with a good connectivity. You don't see a ragged image. Even for lower resolution, this will still hold true. And if you zoom out, you will find that you see very discrete, ordered structures and very flat solvent areas, while the map from the wrong hand hopefully looks more uniform and more ragged in total. Hopefully. Otherwise, you have started to build them both.
If you don't see something like that, don't give up, please.
So we have now done density modification. And we have usually, so in SHELXC we have used SHELXC to do that. So we have now basically solved the structure and can start building in that map. So I'll now talk about practicalities. Things that you should possibly take note of when doing this. First thing is, this is heavy atoms that can be used to isomorphous replacement. And you can see there's the classic heavy atoms. And some people also use gases like xenon, often for also anomalous effects they have. There's significant so these are the significant anomalous scatterers from the periodic system, and there's quite a lot more of them. The nicest is that sulfur is in there, so we can use what is actually in the protein. And there is selene for selenium-methionine derivative crystals. And again, there's the gases, and then most heavy atoms also scatter anomalously. So there's more chances in this. For your data collection, high multiplicity is good, but radiation damage is bad. Very often this means you have to attenuate your beam because you are not interested in multiplicity 1, high radiation damage. For experimental phasing, you need a good multiplicity, possibly 4 or something. It depends really on your case. You need precise intensity measurements. So you should make sure that everything you can do to make your intensity measurement precise has been done. Near the absorption edge, the crystal will absorb the most energy. It's called absorption edge, right? So consequently, radiation damage will be maximized. And if you have before collected a native data set at a more inconspicuous wavelength, the radiation damage you have observed there will not necessarily apply to the wavelengths you are now using. A fluorescence scan can prove the presence of anomalous scatterers in the crystal. And you can often do it before you measure. It will also give you an idea of F dash and F double dash. So for MAT, and this is really my opinion on things, there's many other philosophies around on this. And you should definitely not do this because just I said it. You should think whether you would like to do it in this way, and if not, why other? And I'm sure that we can hear more ideas on which should be measured when in this audience or at any given crystallography conference. So the idea is you collect the peak, which is here, with at least a multiplicity of 4. You have radiation damage. After that, stop and try SAT. Use a second crystal to collect high energy remote. High energy remote is here. And then the last data set, in my opinion, should be inflection, because in inflection we care about the F prime contribution. And I don't know if you remember, if you have the structure factor, F prime usually points backwards, making actually FHKL smaller, the real measured FHKL. So if you have radiation damage, you have lost atoms, right? That would make FHKL smaller as well. So we would consequently kind of artificially maximize the effect. Then you can perhaps, if your crystal still is alive, collect a higher resolution data set with a lower redundancy for density modification, because for density modification you need good resolution, and for refinement, where you also want to have resolution like in the LS phase data set. For SAT, the best wavelength is right and not too close to the peak. Why not too close to the peak? Of course, anomalous signal would be very high there, but radiation damage would be as well. Don't hit the white line near the peak. Measure a little bit away from the peak to have less radiation damage. There's very many SAT data sets in the PDB, or some at least, that are measured at peak, and this is usually the result of a mad experiment where the crystal died. Which is, I mean, if they still could phase it, why not? Data evaluation, your general data quality should be good. You need a good multiplicity, good completeness, PIM, all the quality indicators should look good, and you should make sure they look good. If scaling was applied, check your statistics. In particular, if you encounter problems, you want to know what happened in scaling, but you will need it. Check the mask when you do the integration. Again, beam stops, holders of beam stops, everything that casts shadow may produce outliers. And you really don't want anything there what is not a real reflection intensity measurement. Also, you could possibly go for a high inner shell completeness. So at a low resolution range around the beam stop, you want a good completeness. Some people even take another data set, which is only having low resolution for that very purpose. Did you name your files correctly? I mean, because if you do a mad experiments and you confuse your dataset names, you're laughing now, but it's very desperate if it happens. And I've seen it at least once, and it's very bloody. It's no fun.
People call file names new or today's.
Yeah, or test.
That's why the wavelength is recorded in the file.
Yeah, that is true, but I mean, just better make double sure. If you have made a fluorescence scan, keep it. Is there an anomalous signal in the collected data at all? Because if there isn't, you should possibly think about MR, or why didn't it work? So you can find this out if you could calculate something which is called CC anom 1/2. What you do is you have a data set, a SAT data set, with your anomalous signal in it. You split it randomly in half. You get 2 data sets with less multiplicity. Within these data sets, you will be calculating anomalous differences. You do that, and some of them might be in both halves. You compare them to each other, and if they are approximately of the same size, their correlation is good. It means the anomalous signal has a good correlation. You have actually measured it. It's not only experimental error that you're observing. You can plot the average d double prime over sigma, or d prime over sigma, depending on the experiment, whether you do anomalous or isomorphous methods. And there is also a correlation between data sets. So for example, in MAT, you would like to compare peak and high RAM. And you can compare the anomalous differences between the 2 data sets to also have an idea. And of course, all of the correlations among the intensities themselves. These diagnostics, by the way, will be put out by SHELXC. On the text, on the screen, there's only 2 pages of text, and one of those 2 pages will be all these statistics. You want to have an idea about your space group. You want to be knowing which space group do I have, how sure am I of it, and possibly things like pathologies. Do I have twinning? Because if you don't suspect you have twinning, you may possibly not know. How many marker atoms do you expect? I mean, for sulfur set, surely you can calculate the number of sulfurs you expect. So that would be very beneficial when searching for the substructure. Which element? And if there's molecules, which molecules? Disulfides, chloride ions, tantalum bromide clusters? What could be the best resolution cutoff? SHELXC automatically assumes 0.5 more than your actual resolution. So if the resolution is 2.2 angstrom, SHELXC will automatically assume 2.7 angstrom. And many people think the program does some kind of very special refined thing there, but it's actually just 0.5. So if you have a better idea, if you see against the resolution your d double dash contribution and you think, no, it's really only going to 3, please try to cut it 3 and possibly at 2.9 and 3.1. Could any marker atoms fuse into bigger blobs of density? Because if you are cutting your data for the anomalous signal at 2.7 angstrom, all disulfides will have become one blob. So the number of marker atom peaks you're searching for may not be the number of sulfurs, but the number of supersulfurs. Can you merge data from different crystals or measurements or runs? Sometimes this is very beneficial because it actually can smooth out errors. Not in any case, but it's worth a try, in particular if you have trouble phasing. What is your expected solvent content? You can actually calculate it by hand. And what is your residue number? I mean, you should roughly know which protein you're possibly looking at. And this is in SHELXC. So SHELXC, as I said, estimates alpha, does your data analysis, and prepares your files. So your experimental data from XDS or, I don't know, SAINT or SCAR files, anything really, goes into SHELXC. It will put out a native HKL file and one containing the alpha angles and an instruction file for SHELXC. SHELXC will then search for the substructure, will give out a substructure. This format can, by the way, be read into COOT. just as a coordinate file. It's what I've just had open. And SHELXC does the density modification. It can also do tracing in the recent version. So if your computer says, by the way, SHELX 2000, I was recently in some university in Austria and they had 2002, I think. So please download the new version. It can do auto tracing, and if you can trace a structure, given you have really good resolution, better than 2.5 angstrom, and you see a CC of the trace of the backbone that has been built against the native data over 25%, this is a sure indicator your structure has been solved. And many pipelines, like Archimboldo or Ample, are actually using that. Speaking of pipelines, you possibly want to use a pipeline. All these programs are command line based, and we will also today in the tutorial use them command line based, but there is graphical interfaces for them. Very many, often within the synchrotron, belonging to the synchrotron, you possibly want to use them for ease of use. There's the program Anoda for validation. I'll just talk a little bit about it after this. And there's other experimental phasing programs. And if your experimental phasing with SHELXC doesn't work, you should really consider them. In particular, because they might be having a nice GUI, or because you have a problem case and you really want to do something more sophisticated, you want to do better NCS averaging, you want to take errors into account, please consider using other software. A very good list of software can be found in the CCP4 wiki under this address. Yeah, so we are now free, but wait a moment. We have now seen we can calculate electron density maps, we can calculate Patterson maps, we can calculate anomalous Patterson maps. What happens if we now, after we have the phases, take these phases and take the anomalous differences and calculate a map with this? And you actually can do that. And it can help you with identifying atom types, because not all elements scatter anomalously, in particular at a certain wavelength. You can assess radiation damage if you have a before and after data set. And one possibility, if you're using anyway SHELXC, to do this is the program Anoda. It's by far not the only program which can do that. And the maps you get look like this. So this is a relatively good resolution viscotoxin with many disulfides, and actually the anomalous maps shows us their position. So you can see disulfide peaks here, here, and here. But you can also see 4 peaks along here, which are thought to be sulfate in the final refined structure. However, one doesn't have very good anomalous density. What did you think happened there? Would you think this is really a sulfate? Could it possibly be a quarter of a sulfate?
Could be another atom.
Yeah, it could be. Could be another atom. Which atom?
Show me to from minus epsilon.
That's true. So actually I looked at the data and I thought it's possibly only partly occupied, or it's some ion. But it's not a fully occupied sulfate, although it has been refined as such. So doing this can possibly confirm things you have done in refinement and help you actually to confirm all the positions of the disulfide bridges as well. Then you have cases like this, where you have the expected metal atom in the middle, and then you have that. So what is that? Surely there's something else here. There's another metal. We don't know exactly which type. In this case, it could be identified because we had a MAD data set. So the 2 peaks would have different heights at different wavelengths. So we could determine actually what the 2 peaks were. And for radiation damage, you can do this very easily. You just take your files through Anoda and feed them into Qt. The green density refers to the before data set. The red density refers to the after data set. So we see that the disulfide bridge has been there in the before data set, but after radiation damage, these blobs appeared and these vanished. What happened is the disulfide were bridged to each other, and then it was cleaved, and it just went open. So possibly some sulfurs vanished completely, but we can assess this kind of effect with calculating such density. This is another example from the same data set where CO2 was lost. New density showed up here. We don't know exactly what that is. So, to sum it all up, you will possibly recognize the slide. Experimental phasing methods use marker atom substructures of certain elements to solve the phase problem via the phasing equations. Patterson maps can also help. MAD and SAD exploit the anomalous signal from one or more data sets from the same crystal at a certain wavelength. SIR and MIR utilize several heavy atom-soaked derivative crystals. They have to be isomorphous, the derivative crystals, to be utilized. Experimental phase solutions do not define the enantiomorph. After the solution, the map that looks like protein and solvent has to be chosen. I want to thank George Sheldrick, my PhD supervisor, Phil Evans, Randy Reed and Ellie McCoy, who all shared their knowledge, ideas, and material with me. And I also want to thank the Reed and Dean Lab for their support yesterday and critical assessment.
Thank you. No, it was very interesting. Any question? Questions? Yes.
When you do the density modification, you mentioned that once you've identified the solvent region, you do density flipping phases.
Yes.
How does that help? Because you just invert the noise. Why is that beneficial?
What you actually do is you flip it, and later you add the original map to it in the beginning of the next round of density modification, and consequently it gets smoothed out. Both are weighted, so it's a little bit more complicated than that, but the real effect is you take the inverted map and you add the real map on top of it.
Okay. Another question? Why people are so sudden? Yes.
When you showed your anomalous map and the isomorphous map, the isomorphous map was considerably less noisy than the anomalous map. Yeah?
Yes.
Is that a general feature for the students amongst us?
Is this a general?
Are you talking about Patterson map?
The Patterson map, yeah.
And I think that question should be directed to Phil Evans because that picture came from.
Yeah. Well, it depends. I mean, the isomorphous signal is much larger for any atom than the anomalous, so therefore the noise is smaller. However, the isomorphous map is dependent on isomorphism. So if the isomorphism is bad, the anomalous map will be better than the isomorphism. What's particularly reassuring when you do heavy atom soaks and look at the anomalous is if you get maps which look the same, you can believe it. Whereas if they look totally different, you don't know. But, usually these days people just look at the anomalous. But it's important to note that with heavy atoms you always get the anomalous actually. So it's SIR and MIR without the anomalous have always been a bit fictional. They don't really exist. No.
You wanted to ask him a question?
Yes, why can you do math from twin crystals?
Why
does math succeed with twin crystals?
It depends on the type of twinning. What you're really doing when you have a meroidal twin is just you have limited your signal further. So the signal will be smaller, but it will still be there. The anomalous scattering is still within the intensities. It is just that now every intensity is actually the sum of two intensities on top of each other. And that consequently just means that your whole distribution has narrowed down. But if the measurements are accurate and the case is favorable, you can still do it. Pseudo-merohedral is roughly the same. And for non-merohedral, you could deconvolute. You could separate them. And actually, it has been done in one PhD thesis for 2 crystals with SHELXC. So you can actually even solve non-merohedral twins of proteins in a very favorable circumstance with experimental phasing.
I think whole problem is HSA playing between signal and noise, signal to noise ratio. If you have 100% or 50% twinning, then it would be more difficult because then you cannot decompose it at all. Yes. And I think that along these lines, probably you should be aware that Wayne Henderson did very nice work in his group. And if you have a lot of crystals, yes, you can collect data from all those crystals for, let's say, sulfur or selenium, and then group your crystals together and merge them. Then when you are merging, you reduce noise. And signal stays same, so signal to noise ratio becomes larger.
Yes, but I would think that you can't do zero or mirror with twinned crystals, unless the twin fraction is always exactly the same.
To me, that's a separate problem. Yeah. If you have several crystals, the problem becomes even more complicated, because when you have several crystals, for each of them, you may have different twin fractions. And you cannot assume that all of them have exactly the same twin fraction. And
yes.
So that adds additional complications. But for merging data, that may help a lot. If you have many crystals, if you have one crystal, then I don't know if select another protein probably. But if you have many crystals, then you merging data, collecting data from many crystals and merging them may help a lot. It has been proven to help.
Yep,
that way you can avoid radiation damage also. If you have severe radiation damage, then you collect from one crystal, another crystal, third crystal, fourth crystal, and so on, and then merge them. But before merging, you have to group them, that which crystals can be merged.
Yeah.
Okay? That's the same one point I wanted to make. Nothing more than that. Any more questions? Yes.
Maybe a comment, but
you are going to get a star as an active student.
On the radiation damage, you say you can look at it and look at how much is in there, etc. But it's almost too late. In a way, you go home, you process your data, and you say, "Oh, that was bad. I have to go back to the signature." So a more practical approach may be just to systematically decrease the exposure time or attenuate the beam, and keep collecting data set on a different crystal. And then experimentally determine which exposure time gives me a solution.
Yes.
Can I just make a comment about that? Right at the start of that, you said you go home and process your data. That's a really bad thing to do. Process your data while you're collecting it at the synchrotron.
Right.
Never leave it till you get
Yeah, so
instead of staring at it and wondering whether this is a correlation coefficient of 25 or 24 is good enough, just stick it into a probe that can solve the your solution. And if the answer is no, then collect another data set, and increasingly or decreasingly reduce the exposure time.
I think it's a very extremely good point, and all tools are there. By the one of the sub-projects in the CCP4 grant proposal is going to deal exactly with that. That you should be able to solve your structure or to deal with all these problems while you're on synchrotron. You should not go away. You try, let's say, SHELXC doesn't work, another crystal, higher exposure, lower exposure, and try MIR, try molecular replacement. All tools are there. They should be compiled together, and there some more decision-making procedures, and then things you may be able to solve your structure while on synchrotron. Then and you can fire all of us.
This is also something in which, for which SHELXC is often used, because it gives you very concrete answers and it's relatively fast, so it's part of many beamlines. And if that already gives you a solution, people are usually happy, because it can be command line accessed and it will not run very long. In particular, now that it's multiprocessor capable, SHELXC, you can do several million trials in the time of a night, or a few thousand just at beamline. Yeah.
Okay, any more questions? Even our most active students is not asking. Okay, today we'll have a tutorial, and Andrea will give a tutorial on basically SHELXC.
Yes.
You have to download SHELXC on your computer. read them before you come. Otherwise, it will be very difficult.
Yes, and also the files. Everyone should get the files.
Do you all know course website now? Who doesn't know there's a website for course? For our course, I mean, not for any course. Okay, you seem to be tired and you want to have a course, okay? Thank you.